Part 3 of your Newman projection films is aimed to discuss not per se how to derive and draw Newman projections from scratch, but this time, given a Newman projection, how can I determine how stable, low energy, or unstable, high energy, not good, this particular Newman projection shape of a molecule is. So once again, the point of this part of the film is, given a Newman projection, interpret it. How stable or unstable is it? How much pent-up energy is in it? And with that, even give some names for certain shapes or conformers, such as a staggered shape, fully eclipsed, gauche shape, fully eclipsed shape, partly eclipsed shape. So that's what we're not going to be making them from scratch. Nope. We will be interpreting Newman projections, which are already presented and made for us. So in order to travel along that path, we need to set forth some definitions, of course. So the first definition is going to have to it this value of theta. Okay, theta is a Greek letter. It's standing for an angle in degrees. And you know, the degree of a circle is 260 degrees. If I start my finger at the top and trace clockwise or counterclockwise, the finger goes back to the origin. That's 360 degrees that have been traveled. And half of that is 180. All right, so we're talking about angles. So this value of theta is instrumental towards determining how stable or unstable a given Newman projection or shape of a conformer is. So this theta is defined, as you see here, I typed it down, as the protracted angle between the largest size or bulkiest group bonded to the spoke and apart from the largest sized or bulkiest group bonded to the sphere between these two items. That's called theta. So we're picking up right where we left off with making Newman projections from scratch. Now we're going to be, as you see here below, we have 4 Newman projections and we're supposed to interpret them. So in each of these Newman projections, we're given a theta. We're asked to input the degree. And from the degree, the degree and amount will correlate to a certain name, gauche, fully eclipsed, of this Newman projection. So let me just say here that as we get going with this problem, you're looking at the molecule of hexane. Hexane, straight chain, long chain hexane, which is given as a Newman projection. I numbered the main chain for you. Carbon 1, endpoint, carbon 2, vertex. Carbon 3 is the spoke. Carbon 4 is the sphere. Carbon 5 is a vertex. Carbon 6 is the endpoint. So this is hexane, straight chain hexane. And we're looking along carbon 3, carbon 4 bond. Here I have a molecule of hexane, as I indicated, and we're looking along the bond between carbon 3 and carbon 4. This red bond can be rotated freely because sigma bonds can rotate. And I have a different shape. I have a different shape again. This is a different shape. So these shapes have names. So we will uncover that. Go back to the handout if I can hit the right button. So for this confirmation, please take a look at the spoke. Okay, do you know where you're looking? I will trace it in red. You're looking at the spoke now, okay? I'm tracing it in red, this spoke. Tracing it in red. You're looking there. That's called the spoke. And on this spoke, we have an ethyl group, abbreviated ET, a hydrogen, and a hydrogen, HAHB. They're labeled. And the sphere. Do you know where you're looking when it comes to the sphere? I'm tracing the sphere. And these hydrogens here and this ethyl group belongs to the sphere. So please keep these teams, as in sports, these teams, the spoke team and the sphere team, separate. They are separate entities. And you will see throughout this process that it is going to be the spoke carbon, which is rotating. That's moved. And the sphere carbon is kept immobilized. Isn't it just? You don't have to take my word for it. The ethyl group's in the same place, isn't it? The ethyl group's still there. So the sphere ethyl group, as well as its hydrogens, have remained intact throughout in each and every circumstance. But it is the sphere carbons remained, the sphere carbon groups remained intact, sphere intact, whereas the spoke carbons were rotated. And they can do so because sigma bonds can rotate. So I set forth for you the spoke team, the sphere team, and I set forth for you that the spoke carbon is rotating and the sphere carbon is immobilized. We will now define dihedral angles for each of these conformers. And from that, we will have names associated with these conformers. So setting forth some definitions, okay? So you can turn these into index card flashcards if you like. Do you know what the spoke team is? Again, I reiterate, everything I traced in red and circle in red will move, will be on the move. That will move. The rest of it remains intact, immobilized, arrested. Only the red spoke will move. Looking at hexane. I will now protract the angle, and we're looking at protract the angle between the largest size or bulkiest group bond to the spoke, that's the ethyl, and the largest size or bulkiest group bond to the sphere, in this case, another ethyl. So the spoke ethyl is up, protracting. And ask yourself, how many degrees is that? And the answer to that question is 180. That happens when you have one which is due north and one which is due south. They are opposites. That's as far away as two ethyls can get. If you were to turn the spoke carbon 1 degree, now it'd be 179 degrees. It's closer than 180. So 180 degrees is as max apart as these ethyls can get. And this conformation, this amount of degrees correlates into the anti or opposite. Anti is the opposite conformation, where the ethyl groups again are living on opposite sides of the conformation. One's up, one's down. They can't get any further away than that. So 180 degrees is anti. So let's take a look at the next. So again, you can see that the spoke carbon has rotated. The ethyl group used to be straight up. Now look at the ethyl group. It moved, didn't it? Got rotated, and everything got rotated clockwise like a merry-go-round. Look where HB used to live. Now where's HB living? It's over there. So everything got rotated, but the sphere remained intact. Now let's protract from the biggest group on the spoke to the biggest group on the sphere. How much is that bond angle there? how much is that? Wouldn't you say it's over 90 degrees, right? It's greater than 90 degrees. So this is, the computer's kind of frozen here, but that I was saying it was over 90 degrees, and that is going to be 120 degrees. So you would want to type, I'll type again, and if not, I'll have to close out and open up the system again. So let's put in here 120 degrees. That's that protraction there. Thank you. And this would be going by the name partly eclipsed conformation. This is the what shape is this? This is the partly eclipsed shape, partly eclipsed conformation. Why do you need partly? Because an ethyl is directly in front of not another ethyl, but a hydrogen atom. That's what we mean by partly eclipsed. The partly eclipsed conformation, ethyl is directly in front of not another ethyl group, but a hydrogen atom. So I'm sorry about the technical difficulties there, but I will keep going and hope that the computer does not freeze again. And when we're done with this circuit, I will show you the hexane conformation molecular model, how it's going through these different shapes, partly eclipsed. And soon I will tell you which conformation is more stable and which conformation is not as stable, which conformation has lower energy, which conformation has more pent-up strain or higher energy. So let's try this drawing thing again. So once again, we're scoping this dihedral angle. Okay, we're looking at that dihedral angle. The angle between the largest group on the spoke and the largest group on the sphere, which is ethyl in both cases. So once again, we're seeing that the spoke has been rotated clockwise and the sphere remains immobilized. And now let's protract that distance between the largest ethyl on the spoke and the ethyl on the sphere. It's just that angle. It's less than 90 degrees, right? So we're going to record 60 degrees. And this conformation will be known to you as the gauche conformation, where the ethyl groups are 60 degrees apart and staggered. Staggered means not eclipsed or not eclipsed. They're offset. Staggered is to offset. Nothing's eclipsed. And our last conformation finds our ethyl group has been rotated. It started straight up, didn't it? Looky, it started straight up. And it's been going clockwise ever since, like the hands of the Big Ben clock in, London. So now it's here. And so let's record this dihedral angle as, I know it looks like 10, but we're going to record it as 0 degrees. That way everything's visible. And this is our conformation here will be fully eclipsed, if you will. Fully eclipsed, which means that, like we saw over here, for partly eclipsed, ethyl is directly in front of, in particular, another ethyl. That's when it comes to be fully eclipsed. 100 degrees, 180 degrees is the anti. 120 degrees is the partly eclipsed. 60 degrees is the gauche. 0 degrees is the fully eclipsed. The methodical presentation for your benefit. I'll tell you the truth. I did the 2 versions of this. This is the second version, and it's much more comprehensive with cohesion and coherence. So I'm very glad I did this the second time. No, so as we look at these different conformations, anti, partly eclipsed, gauche, fully eclipsed, certain conformations will have certain energies or pent-up energies or strains. Before I would continue with this, I would like to show you the circuit. As I said, here we have hexane, carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. And we started, if you look at your left-hand page here, share screen. Sorry to talk to myself when I do this. We're looking right here. I'll take you through each of these. Ding, 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 ding. Okay, stop share. Okay. My finger is on the spoke carbon. Doing my best to present this to you. The spoke carbon. And as I said, the spoke will move and the sphere will remain the same. This is anti-conformation. Anti. Now I would like to try partly eclipsed. This will go clockwise. Partly eclipsed, go. Having trouble seeing this hydrogen I'm touching? That hydrogen's on the sphere. It's eclipsed. I can't see it too well. Partly eclipsed. Gauche, please. The ethyl groups will be 60 degrees apart. There you go. This is gauche. I am now holding this sphere carbon. This is gauche, 60 degrees apart. Just this angle here is 60 degrees. This angle here is 60 degrees. Fully eclipsed. Go. The sphere carbon remain immobilized. This is fully eclipsed. Fully eclipsed. Each of these conformations is allowed. Certain conformations have more energies than others. So certain of these conformations will have what's called steric strain. That definition is already provided. Also called steric clash. 2 groups are in each other's space. 2 non-bonded groups. The 2 ethyl groups are clashing against each other. They're fighting for the same space. If I was to swing these ethyl groups like this, you hear that? Carbon 1 is hitting carbon 6. Bang, bang, carbon 1, carbon 6. You can hear it. That's steric clash. Sterics, crowding. Can carbon 1 reach carbon 6? Oh, yeah. Do it like this. And clank away. That's sterics. Sterics are aggravated for larger size moieties or groups. A chlorine atom with 17 protons is more steric than a fluorine atom with 9 protons. More bigger in size. An isopropyl group with 3 carbons is more bulky and steric than a methyl group with 1 carbon. So steric is the bulk is the clash. Which, using your critical thinking, which of these conformations, conformation 1, conformation 2, conformation 3, or conformation 4, anti, partly eclipsed, gauche, or fully eclipsed, is suffering from sterics? We'll find out. And torsional strain, torsion is electronic in nature. Torsion means twisting. A snail has body torsion because its body is twisted inside its shell. Torsion is the twisting. So, but in particular, this is a resistance to twisting. It's difficult to twist a bond now, to bond twisting. Recall, how many electrons make up a bond? 2. Each bond is made of 2 electrons. This applies to, the torsion applies to eclipsed conformations. This is evident when bonding electrons on the sphere are electrostatically repelling or electrostatically repel eclipsed bonding electrons on the spoke. So we're talking about eclipsed conformations. This is nicely indicated by a diagram, if I may find it. So, color-coded. So I made this myself. So see the blue? That's sterics for you. This is sterics. You're looking at a totally eclipsed conformation. You see the red? That's torsion, torsional strain, torsional destabilization, torsional strain, torsional destabilization. And this is steric clash. These are isobutyl groups clashing. And these are methyl groups clashing. Which do you think has worse sterics? More or worse? Why do I say worse? Because it's more destabilizing. Sterics. Methyl group smaller. Sterics are there, but they're not as pronounced. Torsional strain is resistance to twisting. How do I mean? If you start with this gauche and try to push it past and beyond eclipsed, you're going to get some fight back if those are a real molecule. I'm going to have to use my biceps and triceps to push this across because these electrons and these bonds are repelling each other. Electrostatic, like 2 north poles of a magnet. So once again, easy. Got push, bench press this bond beyond being eclipsed because there's these electrons here electrostatically repelling. This molecule is beveling. It's beveling. It's these where I'm touching here, these electrons and these bonds are wanting to get apart from each other. That's torsion. Not too comfortable of a situation, is it? Back to our handout, please. I hope I explained that well. Classify each Newman projection according to proper name and theta value. So you can try this. You can hit pause and I'll hold here for 15 seconds and not say anything. Encourage you to try to charge ahead and see if you can. We have 2 isopropyl groups there, right? That's your gauge measurements for the theta. Okay, so start from the isopropyl on the spoke. What's the degree away to the isopropyl on the sphere. 0 degrees is to full eclipse, 60 degrees is to gauche, 120 degrees is to partly eclipsed, and 180 degrees is to anti. So go ahead and see if you can finalize that. Hit pause if you will. I'll wait 15 seconds, 20 seconds. I encourage you to do this. Be an active learner. It's okay to make a mistake. Okay, joining back in. By the way, you're looking at 2,5-dimethyl hexane. I numbered the main chain. You have a branch at carbon 2, branch at carbon 5. So that's this molecule. You can make Newman projections for any molecule you please. Let's get these numbers out of here, though, because we don't need them. From the biggest group on the spoke to the biggest group on the sphere. What's that angle? Kind of tight in there, isn't it? Whoops. Look like they're almost overlapping. Eclipsed, right? Oh, my God. So biggest group on the spoke, the biggest group on the sphere. Biggest group on the spoke to the biggest group on the sphere. I've got the computer problems again. So as I look at the rest, we're going to complete this page here, including the last problem. Hopefully the computer joins us back in a minute. And then there's just a little bit more to do, and you will have met your obligations for Newman projections. So wish me luck as I try to rejoin this, and hopefully it's not overwhelmed. Okay. I don't know about starting here. It's kind of hard. So let's start here, okay? Don't you agree that this bond angle is 0? So we'll say that that's fully eclipsed. And this bond angle here is 180 degrees. That's anti-apart, anti-opposite. You should just write anti, if you will. And I'm just going to use a pencil here, not to tempt the computer. So, all right, I'll try. All right, I'll give it a shot. That bond angle, wouldn't you say that that's less than 90? Right? What would a 90-degree bond angle be? We're really having problems here, and I apologize. So looking to see a 90-degree bond angle. What would it be if it was 90 degrees? You like that, wouldn't it? That's 90 degrees. That cut there's 90 degrees, isn't it? That's what you're seeing in blue there is less than 90 degrees. That's 60 degrees. And the type here, 60 degrees, 60. That was gauche. One of the things you can try to use is a letter G is kind of similar to a number 6 if you turn the G upside down. So G is to 6, gauche. So I mean, if you want to use that, feel free. Some word art. And again, if I was to make this a 90-degree angle from the sphere, that would be like that, wouldn't it? Don't you think that that blue bond, that blue angle is a little bit more than 90? Indeed, it is. It's 120. So this is partly eclipsed. And you can actually see that without maybe having to do the bond angle, because the isopropyl group is in front of a hydrogen, whereas over here, for full eclipse, the isopropyl group is in front of the other isopropyl group. And now we're going to rank, we classify them by proper name and theta. The other part was rank the following projections in order of decreasing energy, most stable on first. Well, let's get our bearings as to sterics. How much crowding is there? There's some crowding. There's some sterics. The sterics between an isopropyl and a hydrogen. This is the worst sterics of all. Two bulky isopropyl groups battling it out. No sterics here at all. No sterics there because it's non-eclipsed. No sterics at all. Nice and stable. Relaxing, nice and stable. And finally, there's some sterics. The two isopropyl groups are 60, so they feel each other. You know, they can sense something's out there, but not too bad. How about torsional strain? Yes, there is eclipsing. There is resistance to twisting. Electrostatic repulsions between the eclipse bonds. There, yes, because the bonds are eclipsed. Electrostatic repulsions. There's no torsion here. Well, that looks like a good case there. Low energy. No torsion there. There's no torsion here. So we're gonna, in decreasing energy, most unstable first. Yes, indeed. This is the most unstable. Most unstable first. Most unstable. That doesn't mean it's not allowed to exist. It is allowed to exist. As a matter of fact, out of 100 molecules, 10 of them will likely exist as a fully eclipsed conformation. The second most unstable can be consulted by looking at this chart. That's why I said 10%. So this is full totally eclipsed 10%. Partly eclipsed is the next, see, 20%. So let's go back here. Put here 2. Gauche. And the most stable of all is anti. So it goes 2, 1, 4, 3. Most unstable. That deserves to be typed out. Forgive my caps. Most unstable. Highest energy. Highest pent up strain. Highest strain. Here we have the most stable shape. Anti. Lowest energy. Lowest pent up strain. Forgive my caps. Thank you. So if we take a look maybe at the butane conformation, this is mole percent at KT. K is called the Boltzmann contribution, the Boltzmann distribution constant, and T is temperature. So if you had 100 molecules, 10 of them would exist as totally eclipsed at any one point in time. Are they frozen? No. So long as the temperature is not freezing 0 degrees Kelvin, This is going to be in flux. It's going to be in motion. This is a moving molecule, which you're just taking pictures of. Snap, snap, picture, light pop to, and you're freezing this molecule at any one point in time. But molecules will exist in certain shapes, and this shape here is the most unstable. This shape I'm showing you now is totally eclipsed. And here is the anti-conformation, the most stable conformation, anti. One methyl is up, the other methyl is down. Anti-conformation, staggered anti. 45 of 100 molecules will exist in this shape. Staggered gauche, you know, this much of a degree separation between. There I got it. A little bit of a background there. That's pretty nice there. Yep. So let's say 25 out of 100 molecules will exist as that shape. And partly eclipsed, where the methyl group is in front of a hydrogen. See the hydrogen here? 20% of molecules exist to that tune. You do not need to know those statistics. So you don't need to know the percentages. You should be able to rank them though. And the last bit of this will be, which pair of Newman projections are the same molecule? Well, this is a different type of question. We're looking for molecular identities. So let's list the groups on the spoke. Take a look at the group on the left. Okay. We're looking at this now. So let's just make a list of groups on the spoke and groups on the sphere, shall we? On the spoke, we have, look carefully, CH3, CH3, H. And on the sphere, we have to be careful here, H, H, H. We really have to look carefully, don't you? Don't you agree? On the sphere, H, H, H. So let's take some, whoops, see, I made a mistake there. So there you go. H. All right. So those are our H's on the sphere. See where this is going? Spoke. For the second one, see it's 3. H, H. I think this is not the same. And the sphere, CH3, H, H. These molecules are not the same. The only question will be, which molecule will the third projection agree with? So maybe you can come up with that answer before I can. All right, and that answer is H3, H, H. There's our answer. And the sphere, CH3, H, H. So these molecules, which I'll box, whoops. These are the same because they have the same groups for the spoke and the sphere. And these are the same because they have the same groups for the spoke and the sphere. That's that. So in all, we learned the definitions for dihedral angle. The angle between the largest group on the spoke and the largest group on the sphere. We associate 180 degrees to anti-conformation, 120 degrees to partly eclipsed conformation shape, 60 degrees to gauche shape, and 0 degrees to fully eclipsed shape, and named as such because the bulky alkyl group is overlapping another bulky alkyl group. We put forth steric strain as clashing, groups fighting for space, groups which are not bonded themselves, still fighting for the same space and air because of this, well, fully eclipsed conformation, and torsional strain, this resistance to twisting due to electron-electron repulsions, which is prevalent in eclipsed molecules. And then we ranked in terms of stability. The anti-conformation is the most stable shape, and the most unstable shape is the fully eclipsed conformation. A lot of pent-up energy. And just as a brief review, I probably have more handouts than I need. So let's just say that's maybe 60. Oh, I think it's 90. 120, 180, retracting. Just getting the students used to angles here. 270, almost made the full circle. So hope you can do this. Can you do this? It's a good practice. You can take this time right now to try this problem. Perfect problem. Nice way to wrap up this session. Nice way to wrap it up. Come full circle, if you'll excuse the pun. All right. Hands off. I'm going to give you 20 seconds to try to get through that, okay? I hope you can get through that. I think it's a very fair problem and very nicely delivered. After this, we just have one little piece left to go, and then you're done with Newman projections. Zero degrees. It looks like to me that in this case, the spoke is immobilized and the sphere is being rotated arbitrarily. $60 degrees, 120 degrees. The A's are apart by 120 degrees. And here we have 180 degrees. Remember what I told you about the 6 and the G? They kind of look alike if you turn one upside down. Gauche. I think that's a very nice hint I came up for you. I came up with for you. Fully eclipsed. One A is in front of another A. This is partly eclipsed. The A's are eclipsed, but they're not eclipsed with each other. But not by each other. And 180 degrees. Anti. They can't get any more far apart than that, can they? They can't get any more far apart than that. Nope. Sorry, I'm trying to get this frame for you here. So. Anti-apart. And I did have one more thing to cover. I believe it was on here. So, example 1. There's some definitions on here I covered. Example 1. Trace the arc of the dihedral angle and estimate its angle. What is this angle here? Is it more or less than 90 degrees? Less. Come on, right? Less. So it's not 0, it's 60. You're looking at a gauche, aren't you? Gauche. Gauche. Example 2. I already covered that. Example 3. 2 Newman projections are below. What Newman projections show the most torsional strain? Torsional. I'm thinking eclipsed. Whichever one is eclipsed, that's it. which show the most steric strain, steric clash, fighting for the same space. In this case, the answer is the same for both. It's going to be the eclipse conformation, which has more torsional strain and more steric strain. The eclipse conformation, each and every time. And that does it for this segment, and I'll catch up with you for segment 4. And thank you.